You might think the deadliest animal hunts in the open or stalks its prey with jaws and claws. Yet every year, nearly 1 million people die from a single unseen bite. It is not snakes, sharks, or even humans. It is the mosquito, a creature so small you do not feel the danger until days later when disease takes hold. Here is how the world's deadliest killer uses stealth, chemistry, and evolution to stay unstoppable. A mosquito lands with barely a sound. Its mouth parts, called the proboscis, are far more than a simple needle. They are a bundle of 6 slender tools working in perfect coordination. At the tip, 2 maxillae act like tiny saws, each lined with nanoscale teeth. These move back and forth, slicing through the skin with such precision and lightness that the force applied is less than the weight of a falling eyelash, just about 20 millionths of a newton. There is no stabbing or tearing. Instead, the maxillae gently separate the skin's layers, making way for the labrum, a single tube that probes ahead, searching for a blood vessel. The labium, a flexible sheath, bends and buckles out of the way, never entering the skin itself. It guides the 6 stillets as they advance, then folds back like a sleeve as the mosquito gets to work. The mandibles stabilize the bundle, while the hypopharynx runs alongside the labrum, ready to deliver saliva. Each movement is guided by microscopic sensors that help the mosquito avoid nerves and pain receptors, making the entry nearly undetectable. In a matter of seconds, the proboscis is deep beneath the surface, perfectly positioned for the next phase, a chemical cocktail that lets the mosquito feed in silence. Mosquito saliva is a molecular toolkit designed to keep blood flowing and nerves quiet. As soon as the hypopharynx reaches a vessel, the mosquito injects a colorless solution packed with proteins. Anticoagulants block clotting, making sure the blood does not thicken or stop. Vasodilators like sialokinin relax the vessel walls, widening the path and drawing more blood to the bite. Apurase, a specialized enzyme, breaks down ATP and ADP, chemical alarms that would otherwise call platelets to plug the wound. But the real trick is in the pain response, or rather its absence. Instead of numbing the nerves like a true anesthetic, mosquito saliva floods the site with proteins that soak up pain signals such as serotonin and histamine. These molecules mop up the body's chemical warnings before they can reach the brain. That is why the initial bite goes unnoticed. The immune system remains quiet for minutes, sometimes hours. Only later, as histamine and other messengers finally build up, does the telltale itch and swelling appear, often 12 to 24 hours after the bite. By then, the mosquito is gone, its meal complete. This chemical cloak is what allows mosquitoes to feed in silence, turning a simple bite into an invisible act of sabotage. Inside the mosquito, a hidden clock begins to tick. When a female draws blood from an infected host, whether it is a person with malaria, dengue, or Zika, she also takes in microscopic hitchhikers. These pathogens cannot be passed on immediately. They face a gauntlet. First, they must survive the harsh environment of the mosquito midgut, then break through tissue barriers and multiply, all while dodging the mosquito immune defenses. Only a fraction make it. Over the next 7 to 14 days, these survivors journey from the gut to the salivary glands, quietly building their numbers. This period is known as the extrinsic incubation period, and it is the silent phase when the mosquito herself is not yet dangerous to others. Most mosquitoes die before this process finishes. Only the oldest, longest-lived females ever become infectious, but those that do now carry a loaded syringe in their mouth parts. With each bite after the incubation window, the pathogens, now amplified, are injected directly into the next human. A single mosquito can take multiple blood meals over her lifetime, spreading disease each time. The entire process happens without any outward sign, turning an ordinary insect into a moving reservoir for some of humanity's deadliest illnesses. The threat is not just the bite, but the invisible chain reactions set in motion days before anyone feels a thing. In cities across the world, mosquitoes have found the perfect breeding grounds hidden in plain sight. A single female can lay up to 300 eggs at a time, scattering them in any bit of standing water, plastic cups, clogged gutters, old tires, rooftop tanks. These eggs are built for survival. Even if a puddle dries up, the eggs can withstand weeks, sometimes months, without water. The moment rain returns, they hatch almost instantly, unleashing a new swarm. The entire life cycle, from egg to biting adult, can be completed in as little as 7 to 10 days when temperatures are warm. In dense urban neighborhoods, thousands of larvae can develop side by side in a single container. Generation after generation stacks up in the same season, multiplying the number of mosquitoes with every rainfall. This reproductive speed turns cities into hatcheries. In places like Rio de Janeiro, surveys have found up to 50% of rooftop water tanks testing positive for mosquito larvae. In Bangkok, water trapped in concrete pillars below train lines becomes a nursery for millions. Each new wave increases the chance that a single infected mosquito will start an outbreak. The denser the population, the faster disease can spread. Heat draws new boundaries for mosquitoes, pushing their reach into places once thought too cold or too high. In the last 40 years, dengue-carrying Aedes mosquitoes have moved 300 kilometers north across Europe, an advance equal to the distance from London to Paris. In the United States, Aedes albopictus arrived in 1985, hidden in shipments of used tires from Nagasaki to Houston. The eggs survived a long journey tucked inside damp rubber, and within a decade the species was found in more than 20 states. Each new patch of warmth or standing water becomes a foothold. As temperatures rise by even a single degree, the season stretches longer, and mosquitoes breed faster, hatching new generations in weeks instead of months. Global travel turns local outbreaks into international threats. Flights from tropical cities can bring infected passengers or even stowaway mosquitoes, starting chains of transmission thousands of kilometers from their origin. In 2015, Recife, Brazil, saw a surge of Zika cases. For one mother there, a single bite during pregnancy changed everything. Her child was born with microcephaly, a condition that demands constant care and reshapes daily life. These stories repeat across continents. As mosquitoes find new homes in cities shaped by climate and commerce, the world is shrinking, and with it, the safe zones from mosquito-borne disease are disappearing. Mosquitoes have survived every weapon thrown at them. Decades of spraying with pyrethroid insecticides once kept malaria in check, but those days are fading fast. In parts of West Africa, more than 90% of Anopheles mosquitoes now shrug off these chemicals. In Burkina Faso, field studies traced a surge in child malaria cases to a simple fact. Bed nets, once a lifesaver, were failing as resistance spread. Mosquitoes adapt with astonishing speed, changing not just their genes, but their behavior. Some now bite during the day or outdoors, slipping past the nets and screens designed for night attacks. Scientists have turned to new tactics. In cities like Cairns and Medellin, teams release mosquitoes infected with Wolbachia bacteria. This microbe blocks viruses like dengue inside the mosquito, and over several years, dengue cases dropped by half or more. In Brazil and Florida, releases of genetically modified Aedes mosquitoes, engineered to produce only doomed offspring, cut local populations by up to 95%. Yet each approach faces limits. Wolbachia does not affect malaria, and releases of genetically modified mosquitoes spark fierce debates over safety and ecological impact. The most ambitious idea is the gene drive, a genetic tool that could spread a trait through wild populations in just a few generations. Lab trials show gene drives can crash mosquito numbers by 90% or more, but evolution finds cracks. Resistant mutations can appear within months. No gene drive has ever been released outside the lab. Regulators and communities weigh the promise of eradication against unknown risks to ecosystems. The arms race continues, each advance matched by a new counter from the mosquito. For now, eradication is out of reach, and the deadliest animal on Earth keeps finding new ways to survive. Every year, over 700,000 lives are lost to a bite, almost too small to notice. As climate change and urbanization expand mosquito territory, the risk grows everywhere. Our struggle with this tiny predator isn't over. The next outbreak may be closer than you think. Stay vigilant.